Chapter 2 is all about the applications of differentiation. So basically, how do we use all of the derivatives that we learned about in Chapter 1? So Section 1 is focusing on something called the first derivative test. And basically what we're going to do is we're going to use derivatives to be able to find the maximum or minimum of functions, as well as determine where a function is increasing or decreasing, and then be able to use that information to sketch a graph. So the first thing here is a definition. A function is increasing over a specific interval if for every a and b in that interval, a is less than b, then f of a is also less than f of b. So basically what that looks like on a graph is if I have some function like this, so this is just a part of a function, and we're looking at two specific points. So let's say this is going to be my A, and this is my B. Then for every value where A is less than B, if you look at the Y values that correspond to these, F of A is also going to be less than F of B. So basically, as you move left to right, you want to think of this almost as like you're going uphill as you move left to right. So then notice too with this, notice if I were to draw tangent lines on here. So if I pick points in between this interval and I were to sketch tangent lines, so if you look here, just picking several tangent lines, you can see that the slopes of all of these tangent lines are always going to be positive. So if a function is increasing, the derivative is always going to be a positive number because remember, derivatives represent the slope. So that's what's noted down here. So in the interval a to b, the slopes of the tangents are positive. Now if we move on to decreasing, so a function is decreasing if for every a less than b, then f of a is greater than f of b. So what that looks like would be something like this. So I have some function, again, we'll say that this is my a value, so f of a is the y value that corresponds to that. And let's say b is over here, so then f of b is the y value that corresponds to my x value of b. So again, just to kind of talk about the definition again, if I move left to right, for every value where a is less than b, my f of a value or my y value is greater than the f of b value. So that's decreasing over that specific interval. I always just think of it, the easiest way is if you move left to right, increasing is going uphill, decreasing is going downhill as you move left to right. So again, thinking of this with the tangents, if I were to draw tangent lines on here, so if you imagine all these tangent lines, the slope of those tangent lines are negative. So whenever you have a decreasing interval, or where a function is decreasing over an interval, the slopes of the tangent lines are going to be negative. So that's what this is saying down here. So that also means that the derivative would be negative because the derivative represents the slope of the tangent. So there's actually a theorem that states all of this. So that's on the next page here. So if f prime of x, so the derivative with respect to x, is greater than 0, then that means in that interval the function is increasing. If the derivative is less than 0, meaning negative, then the function is decreasing over that interval. So if you look at this graph here, we can easily see where the function is increasing versus decreasing. So if you look at the tangents of this, so imagine all these tangent lines on this curve. Over on this side, where I just marked, this is where my function is increasing, which also means this is where the derivative would be a positive number because the slopes of all of these tangents are positive. Notice though at this point right here, my slope is actually equal to 0 because it's a horizontal slope. Now, when I keep moving right here, I get into a section where if I were to draw these tangents, my tangents all have a negative slope. So right here we have a negative slope. So that means the derivative would be less than 0. And then if I look again, my slopes start to go up again, so they start to get positive again, which means my derivatives are positive, which means my function is increasing. So where the derivatives are positive, function is increasing. Where the derivative is negative, the function is decreasing. So in this range here, we have increasing. Then we went to decreasing in this interval. And then again, this last interval was increasing. The function was increasing. Now, keep in mind, I have two spots where my slope is equal to 0. And where the slope is equal to 0 is where the derivative would be equal to 0. These two values would not be included in the explanation of increasing versus decreasing. These two values where x equals -1 and x equals 1, these are actually called critical values because it's like the turning point of your function. We're gonna talk a little bit about maximum and minimums. So these values are actually where the slope is equal to 0, where the derivative is equal to 0, and these are the maximum or minimum points. So these values, so x equals -1 and x equals 1, are called critical values. And we'll talk a little bit about critical values in a minute. But the main thing here is if I were to talk about the increasing or decreasing, so of this function, the function is increasing on the interval from, so we look down here, from -infinity to -1. And you always are going to write increasing or decreasing in open brackets because at these points here, those are critical values and those are not included in the increasing or decreasing. That's where the function changes. So it was increasing from -infinity to -1 and then again at 1 to +infinity. So from 1 to +infinity. The function was decreasing from -1 to +1. So in this interval here. So from -1 to +1. And again, I'm using the parentheses or the round brackets because you are never going to include those horizontal slopes or those slopes that are 0 to the turning points. So increasing and decreasing is always going to be in open intervals. So talking a little bit more about those critical values. So in this picture we saw that -1 and 1 were the critical values. But if we had a picture something like this, we want to talk about the different points here and how they represent critical values. So the first thing is I want you to note that all of these values that I have pointed out are critical values. So C1 through C8 are all critical values. And what makes these critical values is the fact that they're either going to be points such that the derivative is equal to 0, or meaning the slope is a horizontal slope. So the slope is equal to 0 of the tangent line. Or, so there's two cases. One case is when the derivative of that point equals 0. So that's going to be basically all of these situations that have tangent lines that are horizontal. So those would be some examples from this picture. would be C1, C2, C4, C7, and C8. Those are all examples where the derivative would be equal to 0 at those points because the tangent lines have a horizontal slope. Now, the other situation for this is whenever the derivative is not differentiable, meaning the derivative doesn't exist. So where the function is not differentiable is where the derivative does not exist. So if you remember back in chapter 1, where a function is not differentiable is at discontinuities, at vertical tangents, and at corners. Now we're going to assume for this section that all of our functions that we're looking at are continuous. So we're not going to worry about discontinuity at all. So that's just something that we're going to assume for this section. So basically what we're looking at are corners and vertical tangents, and at those specific points, our function may not be differentiable. So looking at this picture, right here I have a vertical tangent. So wherever the derivative does not exist, we also have what are called critical values. So the derivative does not exist at these other points that I'm going to list. So we have our examples are going to be at C3 because it's a vertical tangent, and at C5 because I have a corner, and at C6 I have another corner. So at C5 and C6, those are going to be my corners. So at C3 was a vertical tangent, and we know that derivatives do not exist there. And at C5 and C6, these were corners. So at these critical values, these are points that separate the intervals over which a function changes from increasing to decreasing or from decreasing to increasing. Now, it doesn't always have to change. The function doesn't always have to change from increasing to decreasing at these critical values, but these are the points that we have to check, because if a function is going to go from increasing to decreasing or decreasing to increasing, it's going to occur at these critical values. If you remember the last example, the two critical values were the maximum and the minimums. So in this example, though, if you look at like C3, the function is still going from increasing to increasing, so that critical value isn't going to be that important that we have a vertical tangent there. It's not going to change how the function behaves. So more formally, let me give you the definition of this. So a critical value of a function is any number c in the domain of f for which the tangent line at the specific point is horizontal or for which the derivative does not exist. So if the tangent line is horizontal, that means that the derivative equals 0. If the derivative does not exist, then f prime of c does not exist. However, keeping in mind that when you take c and you plug it into your regular function, it does have to exist. It just can't exist as a derivative. Okay? So when we're looking for critical values, these are the two conditions that we have to satisfy. It's either going to be the derivative set equal to 0, or that the derivative doesn't exist, meaning you have a vertical tangent or you have a corner on your original graph. So the next thing is talking about maximum and minimum values. Now I've already kind of mentioned it, but basically when we're talking about maximum and minimums, we're talking about the peaks and the valleys of a graph. So we're going to focus on, in this section, just relative maximum and minimum values. But let me kind of just show you the difference here. So if I have a graph, the absolute minimum is basically looking at this entire graph and finding the point that has the smallest y value. So this point down here would be the absolute minimum. Now the absolute max means looking at the entire function, find the point that has the highest y value. So this is going to be the absolute max. And again, we're not going to really focus on absolute min or maxes, but just so that you kind of can see the difference. So what we are going to focus on are what are called relative maximum minimums. And what these values are means over a specific interval, find the highest y value or find the lowest y value over a specific interval. With that said, you can never be at an endpoint for a relative max or min because it has to be between an interval, meaning you have to have x values on either side to be looking at. So this absolute max cannot be a relative max because it's an endpoint. There's no y or there's no x values on the right side of it. However, this point right here would be considered a relative max. And the reason why it's a relative maximum is because between certain x values, or between a certain interval, it's the highest y value. Now, I can also say that both of these values here are going to be relative minimums. And the reason why they're both relative minimums is because over different intervals, those are going to be the lowest y values. So just kind of summing up what I just said, relative extrema occur wherever we have a critical value. So wherever the derivative is equal to 0 or the derivative does not exist. So where the tangent line has a slope of 0 or where we have a corner or where we have a vertical tangent. And that's the only place that those are going to occur. Okay, so if you were to look back up here, this would have a tangent line of 0 or slope of 0. This would have a tangent slope of 0. This is a corner, so the derivative does not exist there. Another important thing, which I already talked about, but absolute maxima and minima can occur on endpoints because we're looking at the extrema over the entire function. But keep in mind, relative maxima or minima cannot occur. So they cannot occur on the endpoints of a function because you have to be able to have values on both sides. So more specifically, the definition of this relative minimum is a point where that specific y value is lower than any other y value. Relative maximum at a specific value of c, that y value that corresponds to x equaling c is greater than any other y value in that interval. So the next thing is saying that if a function has a relative extreme value on an open interval, then c is a critical value. So we have the derivative equal to 0 or the derivative does not exist if we have a relative extreme value at that point c. So basically, if there's a relative max or min, then that means that that point is a critical value. However, note that just because a function has a critical value, that doesn't mean that there's always going to be a max or min. So it doesn't go both ways. So if you have a max or min, that implies a critical value, but a critical value doesn't always imply a max or min. But we will be using critical values to kind of eliminate and reduce to see our choices for possible max and min. So it's a way for us to kind of take some specific points and then just use those to test, are they really maximum or minimums? Before we look into that, let me just show you an example that has a critical value but doesn't mean that there's an extreme point. So if I have this example here, this value at this point 1, 2. So at that point 1, 2, I have a horizontal tangent line, which means that the slope is 0, which means that the derivative at that point is 0. So the derivative of 1 would be 0, which means that x equals 1 is a critical value. However, if you look at the actual graph, so if we look at the graph right here, if you imagine my tangent lines, they all have a positive slope. Over on this side, my tangent lines still have a positive slope. So my function continued to increase for this entire graph. It had a positive slope, and never stopped increasing. So therefore, this point 1, 2 is not a max or it's not a min, but it is still a critical value. So it can happen where you can have a critical value that is not a maximum or minimum. Okay, so just keep that in mind. So what we're going to look at now is, well, how can we tell when critical values lead us to relative extrema? So again, if you look at this side of the graph right here, my derivative is going to be negative because my slopes are all negative values. At this point, I have a minimum. This is a relative minimum. But then if you look from here to this relative maximum, the derivatives would all have a positive number because all of the slopes are going to be positive. And then if you look again from here to this minimum point, my derivatives are going to be negative. All of the slopes of these tangent lines would have a negative number, therefore the graph is decreasing. And again, you can go from this side up until this maximum are going to be positive. And then from the maximum down to this point here are going to be negative slopes for the tangent lines, meaning the graph is decreasing there. So let me go back and fill in these points. So we said that this would be a relative minimum. And up here is going to be a relative max. And basically what we're getting at here is what helped us. So notice what changed in the slope. What's the pattern? Where in this example, I went from positive to positive, which told me there was no maximum or minimum at that critical value. Where here, I went from negative, so a negative, to a positive, which meant I had a minimum. So I went negative to positive, which tells me I have a relative minimum. Then I went from positive to negative, which tells me I had a relative max. Then I went from a negative slope to a positive slope, which tells me I had another minimum. Then when I went to a positive slope to a negative slope, that tells me I have a relative max. So basically what happens is if your values or if your graph goes from increasing to decreasing or decreasing to increasing, that means you're going to have a maximum or minimum at that critical value. If your graph just stays increasing to increasing or decreasing to decreasing, you are not going to have a relative max or min at that critical value. So looking at the derivative, whether it's positive or negative, is really going to tell us a lot because it's really telling us a lot about the slope. If it's a negative, it has a negative slope, which means it's decreasing. If it's positive, it has a positive slope, which means it's increasing. So knowing the derivative is actually going to be really helpful because it's telling us a lot about the slope of the tangent, which is telling us if the function is decreasing or increasing on that interval. Knowing these critical values are also really important because it's helping us to break up the graph So we don't have to look at all these different points. We just have to focus on different intervals. So let's actually look at the rules for the first derivative test, which we kind of just talked about, but let's put this in a chart and actually look a little more specifically at these rules. So basically, if we have a graph, we're going to look at 4 different scenarios. So if we have this graph that first would have decreasing, would be decreasing because all of the slopes of the tangents would be negatives. Then it goes to increasing, meaning all the slopes of the tangents are positive. What does that mean? So it means that C is actually going to be a relative minimum. And if you look at the sign, so the sign for x in the interval a to c, well, it was a negative derivative, meaning it was decreasing. So the sign of the derivative would be a negative. The sign in the interval from c to b was a positive. All of the tangent lines have a positive slope. So what that means is we're decreasing in the first interval. So decreasing on the interval a to c, and increasing on the interval c to b. And again, I'm using open brackets because increasing and decreasing, you have to use open brackets because you're not actually including those points. Let's look at the next scenario. The next scenario represents that from a to c, all of my tangent lines would have a positive slope. From c to b, all of my tangent lines would have a negative slope, meaning the derivatives would be negative. So in this case, I have a relative maximum. So from a to c, the derivative was a positive value. So for all derivatives on the interval a to c, you're always going to get a positive value. From c to b, if you evaluated the derivative at any of those points, it's always going to be a negative value, which basically means I'm increasing on the interval a to c and decreasing on the interval c to b. So then let's look at the last 2 situations. What if we have a graph like this? So look at this graph. All of my slopes would be negative, and then all of my slopes are going to stay negative. So if you look, if I have negative to negative, this value at C is not a max or a minimum. So there is no relative max or min in this situation. But what happened? Well, the derivative on the left side of the critical value, all derivatives would have had a negative value. The derivatives on the right side of the critical value would all come out to be a negative number. So that means, since I have derivatives or slopes of negative values, that means my graph is decreasing. And it's decreasing on this entire interval. So on the interval from A to B. And then the last case is, what if you have a graph where you have all positive slopes? So if you were to look at this, all the tangent lines on this side would have a positive slope of that side of the critical value. Then on the other side of the critical value, all of these values would have slopes that are positive. So meaning, again, there's no relative max or min. And on both sides of the critical value, my derivatives would come out to be positive numbers. So what this means is the function is increasing on the entire interval here, on the interval from a to b. So the next thing we need to do is we need to actually look at how does this whole, all these vocab words and this whole first derivative test, how do we actually use this? So let's look at some examples. I have 3 examples to show you. So let's start with this first example here. So our first goal is going to be to find the relative extrema of this function and then use that to sketch a graph. So before we do anything, our first thing that we need to do is we need to just find the derivative because we know that we're going to need the derivative. So let's find the derivative of this function. So we're just going to use the power rule. So 3 times 2 gives me 6x squared minus 2 times 3 gives me 6x, and then it's just going to be minus 12. And then once you have the derivative, so we need to determine where the derivative doesn't exist or where the derivative equals 0 so that we can find the critical values. So remember, the whole point of this first derivative test is to first figure out the critical values. Then once we know those critical values, we're going to be checking intervals to see, is the derivative positive at those values? Is it negative? To determine increasing or decreasing. But we're going to use the critical values to also determine the maximums or minimums. So we have to ask ourselves, where does the derivative not exist? Or is there certain values where it equals 0? So the first thing is we have to look at what kind of function is the derivative. So the derivative is a quadratic, meaning it's continuous and it's going to be evaluated, or you can evaluate it for any real number. So there's not going to be any spots where this derivative won't exist. So that first part we can kind of just forget about. Okay. The next part, though, is where is the derivative equal to 0? So that means I'm going to set this equal to 0. So 6x squared minus 6x minus 12 equals 0. So divide everything by 6. So it makes the factoring a little bit easier. And then from here, we get our 2 factors. So we have x. Remember, add to -1, multiply to -2. Bigger number is going to be negative, smaller number will be positive. Set each piece equal to 0. And then get your solution. So we have x equals 2, x equals -1. So now the next stage, once we get these 2 values, these are our critical values. And we have to use these. So these are the critical values. And we have to use these to be able to figure out the intervals for increasing and decreasing. Remember that the critical values are going to be the only places where your function can change from increasing to decreasing. So we're going to look at these, and what we're going to do is we're going to basically set up a number line with these critical values on it. So I'm going to set up a number line. I'm going to have -1 here, and I'm going to have 2 over here. And you need to check each of these intervals. So there's 3 intervals on our graph that I'm concerned about, because the critical values are going to be the points where the increasing or decreasing can change. They might also be maximum or minimums depending on the pattern for increasing or decreasing. So you need to pick a value in each of these intervals. Try to pick numbers that are easier. So something less than -1 would be -2. So basically what you need to do is you need to plug -2 into the derivative. Remember, you're always going to plug into the derivative because we're looking at if the derivative is positive or negative. then that's going to tell me is my slope of the tangent positive or negative, which will then tell me increasing or decreasing. So we're always going to plug into the derivative. So I plug -2 into the derivative. So it's going to be 6 times -2 squared minus 6 times -2 minus 12. So the value you get when you evaluate this is 24. So 24 is a positive number, which tells me in this interval from -infinity to -1, my graph is going to be increasing because the slopes are going to be positive values because the derivative evaluated at a specific point was a positive value. So then I go to this next section here. And I need to test another number between -1 and 2. So pick a number that's easy to test. 0 is always a nice option if you can use it. So you're going to plug 0 into the derivative. So 6 times 0 minus 12. So the derivative evaluated at 0 is going to be -12, which tells me I have a negative value, which means my slopes of all of my tangent lines are negative, which means that my function is decreasing. And then the last case here, pick a number bigger than 2. So test 4. Doesn't matter which number you pick. So plug in 4 into your derivative, and you're going to end up with 60 when you do that. So again, you get a positive value, which tells me my slopes are positive of my tangent lines, which means my function is increasing from 2 to infinity. So we know the general pattern here, the general shape of my graph, but now we can decide, are these critical values, are -1 and 2, are they maximum minimums? So what you need to look at is I went from increasing to decreasing. So that tells me that critical value is going to be a maximum. Then over here, I went from decreasing to increasing, which tells me my critical value of 2 is going to be a minimum. So a minimum at x equals 2. Okay, so you have to think about the actual shape, or this is kind of using that chart on the previous page too. So now the question is, how do we actually use these to plot some points and to come up with a graph? So that's the first derivative test, but now let's use these to come up with a graph. So the first step, let's find the relative maximum. And remember, we said that this occurred at x equals -1 based on our increasing and decreasing pattern. So in order to figure out the maximum, that means find the point. So take -1, plug it into the original function. We're looking at the maximum of the original function, no longer the derivative. The derivative is just to tell us increasing or decreasing because of the slope. So now I'm taking -1, I plug it into the original function. So -1 to the third minus 3, -1 squared minus 12 times -1 plus 12 is equal to 19. So that tells me the point for the maximum is going to be -1, 19. We do the same exact thing for the relative minimum. So the relative minimum we said is at the point x equals 2. So we're going to plug 2 into the function. So we have 2 times 2 to the third minus 3 times 2 squared minus 12 times 2 plus 12 is going to all come out to be -8. So that tells me my relative minimum is at the point 2, -8. So now, lastly, to sketch this graph, you're going to use these 2 points. I know that those are 2 points, and I know the general shape goes from increasing to decreasing to back to increasing. So looking at the graph, start by first sketching those 2 points. So we have -1, 19. So -1 somewhere up here at 19. Then we go to 2, and we're down here somewhere at -8. And remember, the general shape of my graph has to increase up to this point. So it's increasing up to that point. Then it's going to decrease until I get to this point. And then it's going to begin increasing again. And that's because of the way the derivatives work. So remember, the derivatives went from positive to negative between that interval of -1 to 2, and then they went to positive again from 2 on. So this is just a rough sketch. If you wanted to find more points, then you would just plot some extra points, but this just kind of gives you a rough idea of what the graph should look like. So let's do another example just to kind of give you a feel for this. So let's look at another one. So for this one, we want to find the relative extrema of the function 2x to the third minus x to the fourth, and then sketch this graph. Remember, the first step here is always going to be find the derivative. So it's going to be 6x squared minus 4x to the third using the power rule. Now, we have to decide where the critical values are. So first of all, figure out if there's any values where the derivative does not exist. Well, if you look at the derivative, it's a polynomial again, so polynomials are continuous. It's going to exist for all real numbers. The derivative will exist for all real numbers. The second thing then is to find your x values where the derivative equals 0. So that's what's under here. So this is kind of the process you run through. You say, okay, find the derivative. Well, the derivative exists for all real numbers, so can't use any values from that for critical values. So now I set the derivative equal to 0, and we solve for x. So set the derivative equal to 0 and solve for x. So go ahead and factor out a 2x squared. So I have 3 minus 2x equals 0. Set both parts equal to 0. And solve for x. So here I'm going to get x equals 0. Over here I'm going to have 3 equals 2x. So 3 over 2 equals x. So again, these are my critical values. Those are the only points that could have maximums or minimums at them, as well as the only points where your function is going to change from increasing to decreasing. So at the next step, this is where we're going to set up our number line, and you're going to have your 3 intervals. So I have x equaling 0 as a critical value and 3/2 as a critical value. So pick points to test. So I'll test something less than 0. So let's say -1 is a value in this interval. And again, when you test your values, they are going into the derivative. You're trying to see if you get a positive or negative value for the derivative, which really is representing the slope of the tangent. So if it's a positive slope, it'll be increasing on that interval. If it's a negative derivative, it means it's a negative slope, which means your function's decreasing. So I plug in -1 into my derivative function. And we get 10. So we get a positive number, which tells me my function is increasing from negative infinity to 0. Then we go to the next section. So then we test a value between 0 and 3/2. So testing 1 would be convenient. So let's test the point 1. So again, plugging into the derivative. So 6 times 1 squared minus 4 times 1 to the third. The derivative comes out to be 2. So it's a positive number, which tells me my function is increasing in the interval between 0 and 3/2. So last section we have to test is the section where from 3/2 to positive infinity. So pick a number bigger than 3/2. 3/2 is like 1.5. So how about 2? So let's test the point 2. So plug into the derivative. So we have the derivative at 2 is equal to -8. So now we have a negative value, which tells me my function is decreasing. So now looking at this between the critical values, you want to ask yourself, well, what's really happening? So in this case, my function is going from increasing to increasing, which is telling me since there's a critical value at 0, kind of tells me that my function is going to be like leveling off and then coming back up. So it's going to be a case where there's going to be a tangent line at x equals 0. So just kind of keep that in mind when we go to sketch. So it'll be something like this, basically, in this range here. And then we go to this next step. It's increasing, and then it starts to decrease, which means I'm going to have at x equals 3/2, there's going to be a maximum. So here, I'm not going to have any relative mins or max, but I am going to have a tangent line at x equals 0 with a horizontal slope. That's basically why there's a critical value at that point. So let's go and evaluate and figure out the maximum. So figuring out the maximum is our next step. So we're going to find the max at x equals 3/2. And remember, to do that, you're plugging in the 3/2 into the original function. It's always into the original when you're trying to find a max or min. So I plug in 3/2 into the original, and you get 27/16, which means my point is going to be 3/2, comma 27/16. That's going to be my relative max. So when I go to graph this, you want to basically start with that point, with your maximum point. So roughly that's going to be somewhere in here will be that maximum point. So this would be the max 3/2, 27/16. And remember what we said, the graph went from increasing to then decreasing at this point. So we also said that at 0, there was going to be a horizontal tangent. So it's kind of where your graph is going to increase, it's going to level off, and then it's going to begin to increase again. That's why we have that critical value at x equals 0. So this is kind of a rough sketch. And you can even evaluate. So at x equaling 0, we know we're going to have some leveling off, but we also need to know the y value. And I kind of already did that ahead, knowing that when I plug in 0 into my function, I'm going to get out a y value of 0. So that's how I know the intersection is really at 0, 0, where my function starts to level out. But you could actually test that. So like if I were to, let me just make note of that, at x equals 0, there is a horizontal tangent. So that means, so this is because f prime of 0 is equal to 0. So that means if I take f of 0 of my original function, so plug 0 into your original function, you get 0. So that's kind of how I knew at the point 0, 0, that's where my function's going to level off. And it's going to have that horizontal tangent. Okay, so again, you could plot some more points, look for the x-intercepts, y-intercepts, those are all good points. But for right now, we're really just focusing on how do we use this first derivative test to kind of help us get a brief sketch of the graph. So let's look at one last example, and then we're done for this. And this example kind of has something different happening, so that's why I wanted to show this to you. So we're going to find the relative extrema of this function and then sketch its graph. So the first thing is we're going to take the derivative. So the derivative of this function, we're going to have to use the chain rule here. So we're going to take the 2/3, that's going to come down in front as a coefficient, keep the x minus 2 as is, subtract 1 from the 2/3. So 2/3 minus 1 is going to give me negative 1/3. And then remember, you always multiply by the derivative of the inside, which is just going to be a 1 when you take the derivative of x minus 2. And then the plus 1 is just going to go to 0. So basically, if I were to rewrite this, this is the same thing as saying 2 over 3 to the cube root of x minus 2. Because the negative 1/3 exponent means that it's the cube root in the denominator. So then we have to consider, where is there any points where this derivative doesn't exist? Or are there any points where this derivative equals 0? So any of those two conditions being satisfied means we're going to have critical values. So when we're looking at this, we can first see that since we have a fraction, we have something in the denominator, this is a good indication that you might have some issues with numbers existing. So if you imagine plugging 2 into this derivative, you would get 0 in the denominator, which means the derivative would be undefined, or this function would be undefined when x equals 2. So that tells me x equaling 2 is actually going to be a critical value because it's a point where the derivative doesn't exist, but if I plug 2 into the original function, it does exist. So that's an important piece though. 2 has to exist in the original function because 2 minus 2 raised to the 2/3 is just going to be 0. So 2 exists in the original function, but it does not exist in the derivative because now I have 2 going into the denominator, which creates 0 in the denominator. So that means 2 is going to be a critical value. The next piece that I have to look at is, what about setting the derivative equal to 0? So in this case, if I take my derivative and set it equal to 0, really the only way that you can take something, 2 divided by 3 times the cube root of x minus 2, and get that to equal 0 is if you have 0 in the numerator. In the numerator being 0, 0 divided by anything is the only way that you're going to get 0 out. So 2, it would be like me saying that take the numerator, set it equal to 0, and 2 does not equal 0. So that means that there is no solution to the derivative equaling 0. So it's kind of summed up down here. So with that said, we've already found our critical values. And now, so my critical value is x equals 2 from this description. So now I just have to put that on a number line. And it actually is nice because now I only have 2 intervals to check. So 2 is the only critical value. So we're going to test a number on the left of 2. Let's say 0. That's an easy number to plug in. We're going to plug that into the derivative. So 2/3 0 minus 2 to the negative 1/3. And you're going to get some negative decimal. So negative 0.529, something like that. And basically what you need to get out is that the value is negative, which means my graph is decreasing from negative infinity to 2. Okay? Then I go over here, and I'm going to test a number. So how about we test 3? So take 3, plug it into the derivative. So you get 2/3 for this. So you get a positive number, which means your function is increasing here. So we went from a decreasing to an increasing function, which means that you have a minimum at x equals 2. Now keep in mind that critical value at x equaling 2 is not going to be a rounded point because we said x equaling 2 is where the derivative does not exist, which means the function is not differentiable at that point, which means that it's got to either be a vertical tangent or a corner. And we know that vertical tangents, so going back to this chart, vertical tangents really aren't going to be that helpful for critical values because vertical tangents are occurring in these two cases wherever you have, like, because it could be something a little bit narrower. So a vertical tangent is really just going to mean that your function is going to keep decreasing or keep increasing. So vertical tangents aren't going to be that important for critical values. Like here's another example of a vertical tangent. So basically, if the derivative doesn't exist or the function is not differentiable at that point, what that really means is you have a corner at that point. So at the point x equals 2, it's going to be a relative min, but it's also going to be a corner since that's the only type of issue that we have with not being differentiable that actually is going to change decreasing, increasing. So when I go to graph this, I'm going to first need to find the relative min at x equals 2. So you're going to do that by plugging 2 into the original function. So we're going to get 1, which tells me the point is going to be 2, 1. And then we go to graph it. So last thing is to graph. So we have 2, 1. That's where this minimum is going to be. And then remember, there's a corner here. So my function went from decreasing to increasing. And I have a corner, so it kind of comes down into like a V shape. So this is just a rough sketch of the function, but you get the main ideas. Okay, so again, your minimum has to be a corner because of the fact that x equals 2 is where the function was not differentiable. So then that's it for this section. And next section is going to be focusing on the second derivative test. So we'll look at that next class.